In this video, I want to talk about phase sensitive detection. I want to actually get into, I think we have done all the preliminaries that were required to understand phase sensitive detection. And in this video, I want to really talk about phase sensitive detection and how we actually preserve the phase when we are uh, looking at, especially with differential sensors. So we've looked at the output of a differential sensor, which is given by the equation on the screen here. And we've seen that the output has two sine waves associated with it. And these sine waves have a frequency of Fc minus Fs and Fc plus Fs. So if you plot that in the frequency domain, you have a spike at Fc plus Fs and a spike at Fc minus Fs, and you do not have any carrier spike. So the carrier is suppressed. And it is in this case, the case where we are using a differential sensor where phase is lost. So how do we preserve the phase? At the heart of phase sensitive detection, we have a multiplier as shown on the screen. So this is a multiplier. The input to the multiplier is the output of your signal conditioning circuit, right, which we looked at in the previous slide. And you take another signal, which is called the reference voltage here. And this reference voltage is the same as the frequency input, as the signal that you inputted to your voltage divider or to your AC bridge. And you multiply this reference voltage with the output to get a signal called Vp. So what we'll do next is we'll just write some equations to think through what happens when you do this multiplication. So if you write the equations, so take a look at this V output. This is the same as before. In the previous slides, we looked at this. So you multiply this V output with a reference signal, and the reference signal is given here by VE cos 2 pi FCT, which is basically the carrier signal, the input to your AC bridge, right? Now, if you multiply both these, what do you get? This cos term and this cos term give you one term, and this cos term along with this give you the second term. Let's write the amplitude as A, and if you see here, the amplitude A is equal to VE x over 4 times VE. So it's basically VE square x over 4. So A is proportional to this amplitude x that we are trying to measure, right? Okay, if you combine these two multiplicative cos terms, so using the formula, there is a trigonometric formula for cos A times cos B, and you get terms of cos A plus B over 2 and cos A minus B over 2. So that's what we've done here. So you get this big, huge term here. Now let's kind of analyze that term in the next slide. So this is the output that we have, and if you just kind of switch over the terms, combine different terms together, so you can see that you have a sinusoid which has a frequency of Fs here, and you have a sinusoid which has a frequency of Fs here. So let's put them two together, and then you have a term which has twice Fc minus Fs and twice Fc plus Fs. So let's put them together, and let's now look at this signal in the frequency domain. So what do we get? So we have one spike at frequency Fs, which consists of these two sinusoids. So you have one spike here, and you have two spikes, one corresponding to twice Fc minus Fs and one corresponding to twice Fc plus Fs. So this is Fc, twice of Fc, and you have one spike here and another spike here, right? So that's the frequency domain picture. Now we know that twice Fc is much larger than Fs. If you remember, when we talked about amplitude modulation, we said in a sensor what we want is our carrier frequency to be much higher than the frequency of the change of physical quantity that we are measuring, which is Fs. So basically you can cut off these two signals by using a low pass filter. So if you put a low pass filter here, these two signals are going to be cut off completely and only Fs is going to remain. Okay, and so if you do that, what are you going to get? You're going to get a signal which has an amplitude of a, as we saw previously, is proportional to x, which is the amplitude of your physical quantity, and you have Fs as well, which is the frequency of the amplitude. Okay, so excuse me. So what we are saying is that the output, uh, which is Ve x over 2, is multiplied with the carrier signal, and the product is low pass filtered, and what we get at the output is xt multiplied by some constant a. So you get the same signal and some uh, with its amplitude modified, okay, which kind of gives you a output that is proportional to the physical quantity that you were trying to measure. So let's just kind of look at the overall signal conditioning of this circuit. So you have a sensor and a signal conditioning circuit associated with the sensor, which takes one of the inputs to this is going to be a sine wave, which is going to be a sine wave of a much higher frequency than the physical quantity that we're measuring. That's going to give an output. Maybe, perhaps, if you want, you can amplify that output. And then you multiply this output with the same signal that you were giving as an input to your sensor again, and pass it through a low pass filter, and at the output you get a signal which has the same shape as the physical quantity that you're trying to measure.